I just shared it. Is it okay?
So just wonder if everyone can mute while James is talking, right?
Yeah.
Yeah.
You can hear me, right?
We can hear you. I don't see the screen. Maybe it's my problem.
Oh, sorry. Let me see.
By the way, I'm very happy that you accepted to give a keynote for us.
By the way, the keynote is being recorded. We'll plan to the keynotes online.
Yeah.
So just FYI for everybody.
So let me say a few words about, I'm very happy to introduce Professor James Joshi. He's a professor of School of Computing and Information at the University of Pittsburgh, and is a founder and director of the Laboratory Education Research and Security Assured Information System. He's currently serving as NSA's Program Director in Computer Network System Division and in the Secure and Trustworthy Cyberspace Program. He's elected fellow of the Society of Information Use and Integration and a senior member of IEEE and distinguished member of ACM. I'm really happy to see the title of this keynote because I'm sure it's going to be very interesting. And today is going to talk about privacy preserving access control and authority transparency. Let the room to him. Thanks.
Well, thank you, Barbara, very much for the nice introduction. So let me take a moment to thank Barbara and Murat for inviting me, as well as Professor Thoraisingham and Professor Rusev for inviting me to be a keynote here. It's also my first time giving a keynote online, so I'm not so much familiar with the etiquette, but I'll try to keep it up. And I would like to congratulate the CODASPY team for having done for 10 years, very successful progress. And also all the team, all the organizing committees, training committee members for the great job done. I'll be talking about privacy preserving access control and authority transparency work that we recently did. Okay, so this is the outline of the talk. I'll briefly overview access control and then talk about our work on privacy preserving ABAC for cloud computing particularly, and briefly share some thoughts on authority transparency with some work that we have done, summarize the talk and discuss some challenges. I would like to take about 5 minutes to quickly overview SATC. I'm taking this as an opportunity for NSF outreach as well. So access control is a very critical component of any secure system. And we are all familiar with that. It's one of the foundation for a secure system. And in the simplest way, we're talking about someone trying to access a resource that needs to be protected and made sure that it is accessed by authorized people only. So it's a logical component that we create access control mechanism based on some models to receive the access for an object from a subject, and then we enforce the rules and provide the authorization decision to the subject. And there has been a tremendous amount of work in this area from the very early days of computing. A lot of the initial work were focused on discretionary access control models, where we're talking about someone having some rights on an object, being able to distribute the rights he has to others. So he has the discretionary power to do that. And then there were significant work done on mandatory access control area, where systems enforce specific rules. And so discretionary access control, there have been a lot of theoretical work based on access control matrix model and so forth. Mandatory access control models, sometimes also called lattice-based access control model, try to address the specific needs for confidentiality and integrity for example, in Bell-LaPadula model and so forth. Around the 90s, there was a huge momentum in the research area for role-based access control as more and more organizations adopted organization-wide systems. And it made sense to think about providing access to resources based on what kind of roles, what kind of duty or responsibility someone has to fulfill within that context. And so ABAC was a huge area of interest for a lot of us. So I had spent a lot of time doing research in that area. There were many variants, many extensions of basic ABAC models, and the founders of ABAC concepts are part of the founders of this conference, Ravi Sandhu and others. Now, more recently, we see a lot of attention given to attribute-based access control. So the goal here is try to address the issue about how to provide access to resources based on the set of attributes and the values that are associated with a particular subject. And we may be considering attributes of objects, attributes that define environmental conditions, and define conditions on these. So that provides a very fluid, very fine-grained approach to addressing access control requirements. So ABAC provides dynamic aspects because we are making decisions based on attribute values that needs to be satisfied at the time request is being made. It is contextual in the sense that you can integrate environmental attributes or conditions in the authorization policies. And it's very fine-grained in the sense that you can have any combination of attributes using logical connectives. So there has been a lot of work in this direction. Taking a side step, we're also seeing this huge development in cloud computing. It has been several years now. A lot of organizations are adopting cloud computing, and because of COVID that we are facing right now, there has been significant acceleration in the cloud adoption. So I was taking some reports, and so in one of the surveys, more than half, 59% said that cloud usage will be higher than planned before the pandemic hit. So pandemic provided the context to really understand the importance of cloud computing, as many felt that cloud turned out to be a lifesaver for businesses. And we are using cloud in some form in this interaction as well. So there are a lot of data being pushed out to be stored in cloud, and now we have to worry about how to deal with this data being stored in an outsourced third-party environment. And that's the focus of this talk. There's a lot of attribute-based access control work focused on different areas. We were a little bit interested on the cloud computing platform, and it turned out to be one of the very important areas, especially from this pandemic context as well. The key issue here is security and privacy. We are putting out data that may have very privacy sensitive information out in the cloud, and how do we ensure privacy about that? How do we provide access to these data items to different groups of users? So that's the focus of this talk, and we need encryption in some form at some point because we need to protect the data in the cloud. And if you consider cloud as a potential threat, typically we consider honest but curious model, where we are assuming that the cloud service provider is honest in carrying out its duties, carrying out the protocols and so on, but may be curious to learn about the privacy sensitive information stored there. So some form of encryption becomes a necessity. But we are also interested in encrypting the data, but also allowing it access to different sets of users. And so combination of encryption and attribute-based access control is one more current approach that a lot of researchers have focused on. So use attribute-based encryption is one current direction, and we were interested in this. So this is really our, among the first applied crypto work that we did in the attribute-based encryption area. Quick background on this area. There had been a lot of work in identity-based encryption much early. In 1984, there was a paper related to identity-based encryption where identities such as email address could be used to encrypt the data, and only the person who owns the email address would have the private key to see the data. And building on this identity-based encryption, several others have proposed attribute-based encryption. Now, instead of just using ID, make ID as an attribute and add other attributes to make public key, private key kind of situation that helps in defining some kind of policy to provide access to the encrypted data. And there has been two types of attribute-based encryption proposed in the literature: Key-Policy-ABE and Ciphertext-Policy-ABE. They're kind of opposite in the sense that in Key-Policy attribute-based encryption, ciphertexts are actually associated with some sets of descriptive attributes, and users' keys are essentially associated with the policies. So, and on the other hand, Ciphertext-Policy-ABE attribute-based encryption is related to subject having a set of attributes in the form of a policy and using that policy to encrypt the data. And any user who wants to be able to see that needs to show that he has the required set of attributes. But there were several limitations or challenges with regards to CP-ABE that we actually were interested in. One is a limitation of original CP-ABE schemes where the focus was primarily on read access. And typically write access, policy update were not there addressed in an integrated way. And there were also CP-ABE, no CP-ABE scheme that supported both immediate attribute revocation and some protection on the policies structure itself. So access structure actually encapsulates the policy defined by the data owner while encrypting the data, and preserving the policy itself was a concern. So we wanted to integrate these features. At the same time, if we are talking about cloud computing, it's a third-party outsourced environment, and anyone accessing data needs to also worry about privacy from access patterns perspective. So when people are accessing data from the cloud server, you want to make sure that cloud itself, as honest but curious, or someone observing the access pattern, is not able to figure out what type of data is being accessed. So even in encrypted form, there has been work that showed that people looking at access patterns would be able to figure out that this particular set of accesses relate to health data. And he can build that, an adversary can build that basic information to leverage, do further activities to understand the actual nature of the data. So it may be associating that data with particular hospital or physician, and then use other techniques like social engineering, brute force attacks to try to figure out the person who is accessing. It may reveal some privacy sensitive data such as diseases because someone is accessing this particular data. It reflects certain disease. Another issue is storage. From the cloud service provider's perspective, making sure while they are serving the clients and they are in encrypted form, the CSPs want to make sure that the storage is not duplicated. Same files, one particular file is not stored multiple times. So data deduplication issue is another concern because we're trying to provide write access as well, policy updates and so forth. There's potential to have duplication issues. So we wanted to integrate that also. And deduplication is a straightforward issue. If you have server nodes in the cloud platform that has different files stored, in two different nodes, there could be same file stored. And instead of having the duplicates, you could just have a reference. And when we talk about encrypted data, that becomes a little bit of challenge because if different people use different keys to encrypt the data, figuring out that stored ciphertext encrypted data are the same would be difficult. And even if it is possible, then decryption, which one do you maintain is concerned. So it's not a feasible idea. But people have done different work to figure out how to achieve deduplication. There's some work on convergent encryption, message lock encryption proposed based on actually convergent encryption itself. So the key idea here is encrypt the data using the hash of that data as key. So if you do the encryption, if everyone does that by using H of D or hash of that particular data is key, then you would get the same and you could figure out which are duplicates. But people have shown that that's not resistant to brute force attacks. And there are other proposals like server-aided MLE that brings in a key server that can provide random secret factors that could be integrated with this basic mechanism to make it stronger. So what we were interested on is to integrate these techniques within our framework. But when we integrate, we have to make sure there are appropriate protocols. For instance, if data owner needs to update the data or update the policy, he has to prove the ownership right. So there needs to be appropriate protocol for that. And also, if someone needs to write that particular data, change it, he needs to prove the right permission that he has on that particular data. So based on these requirements, we tried to work on this integrated privacy preserving ABAC that supports secure deduplication and access pattern privacy in collaboration with my student and colleague, Dr. Krishnamurthy. So overview of that integrated framework, it has different pieces. So it's kind of integration work besides these smaller pieces of innovative components that we try to add. First is the basic PR-CP-ABE, which includes, which is basically privacy preserving revocable CP-ABE. One thing I forgot to mention is we also wanted to support immediate revocation. And also support privacy preserving access structure. Access structure encapsulates the policy, and we want to make sure cloud server doesn't figure out what the policy detail is. The second part is secure deduplication. So we needed to create effective, efficient outsourced data model to support that. And we borrowed this server-aided MLE mechanism to be integrated in the framework. It also needs to be supported by proof of right access and proof of ownership components. And then lastly, to support right and ownership, ownership basically is related to updating the policies. We also borrowed the access pattern privacy related solution, basically path ORAN, and extended it to integrate in the system. And using this extended path ORAN, we were able to support the right operation, the ownership proof and related operation. And this also extended privacy preserving access pattern by default. So overall integrated framework is captured here. There are several pieces. We have outsourced data model, the basic PR-CP-ABE scheme that provides read access, proof of right and ownership components, server-aided MLE, extended path ORAN within that component, and then trusted third-party is there to provide support for public parameters and key services. So here's a quick run through of the process. Owner gets the public key parameters, carries out some encryption operations. For that, it uses message-derived key, which is based on server-added MLE. There's a tag created, which I will explain later. And based on that, so once you use this message-derived key to encrypt the data here, now you use the access structure to create an encrypted data item here, which is now pushed to the cloud server. When it is pushed, so it could involve deduplication check. And so to support the deduplication, it has, we have this outsourced data model that is there. So once the deduplication check is done and avoided, it is updated and kept at cloud service provider. If a user wants to access it, it has to first get the key from the authority and then download the element, the encrypted element from cloud service provider, but there are other mechanisms that is related to the basic PR-CP-ABE scheme that involves decrypting the message first and then using the symmetric decryption key associated with this message-derived key to extract the actual data. So that in a nutshell is the overall integrated framework. And so basic PR-CP-ABE scheme is built on Ciphertext-Policy Attribute-based encryption, which typically has these 4 steps. So first step is setup, where trusted third party sets up the basic parameters. It creates a master key, a secret key, and then creates a public key parameter set that is transferred to actually data owners as well as cloud service provider and users. So it is sent to data owner who needs to encrypt its data. So it uses an access policy, which could be of this form. So it basically says if someone is from CS department and is a PhD student or alumni, he or she could access this data. So by using these 3 pieces, it carries out encryption operation, which is the second step, and then it sends this to the storage server in the cloud with the access policy. So access structure, which we try to make sure is privacy preserving. And then if your users come with different attributes, for example, this one has CS and PhD attribute, which actually fulfills this access requirement, policy requirement. So they communicate with the trusted third party to get the required keys, and then they interact with the service, cloud service provider to get these. And the first one satisfies P, so he gets access. The second one does not. So that's how CP-ABE works. We extend that to include privacy preserving access structure and other operations. So access structure, there has been typically 3 types that have been used: AND gate simply, that is basically expression where AND connectives are used. And then tree-based, which we have already seen an example of. And more recently, a popular one, which is linear secret sharing scheme matrix, where you have a matrix that helps you do sharing of a secret among multiple parties. And this has been found to be very efficient. So we adopt that and try to make it privacy preserving. So linear secret sharing scheme has been there for quite some time. It essentially is share generating, it has a share generating matrix, L by N. And then there's a function that maps each row to a particular party. And then if they need to share a secret S, and there's this process for sharing as shown here, I won't go into detail. And there's a recovery process to extract S by the party. So towards achieving privacy preserving access structure, we use LSS in a simplified modification form. So we have this access policy, for instance. We have this actually on the data owner side, and this could be the actual policy that is used to encrypt the data. So with ID, there is a social security number, specific, you can say this person can access. But when you send the access structure to the cloud service provider, you don't want to provide these details. So you just use these to generate the required public key parameters and encryption operations, but you send only this to the cloud service provider. So cloud service provider would not have the details of the actual values. And we use the property of composite order bilinear groups to support in this particular mechanism. So in the encryption, it helps you introduce random elements from particular subgroup to perturb or hide the attributes, related ciphertext components, and decryption. This property helps you eliminate that random elements so that the appropriate element can be extracted. And we also have a re-encrypt scheme where initial secret is divided into two parts, one for user and the other is for CSP as a delegation key. So this is an instance of how PR-CP-ABE works. First, in the setup phase, trusted third party sends the public key parameters to all the other parties. That includes data owner, cloud storage provider, as well as users. And then the data owner encrypts it by using this access structure and then sends it to cloud storage. But as you see here, the access structure attached is not the same. It does not include the actual value. So that's the level of privacy we get. And then when the user wants to access this particular data, it has to interact with the trusted third-party authority to get the appropriate keys. So it has to send the attributes that it has, and based on those attributes, the authority will compute two keys, SK1 and SK2, as mentioned in the earlier slide. And cloud storage actually re-encrypts that encrypted data with SK2 and sends it to the user. Now user needs to decrypt that using SK1, and then afterwards by the decryption key related to PR. So first decrypt using this SK1, and then decrypt the actual encrypted data using the Mrs. derived key that was mentioned earlier. So outsourced data model is a small but important piece of this, this mechanism we have tried to do. So it has two parts, the metadata part that has essentially the access structures related to that particular data item. So for read, for write, or ownership. And then there's a reference to the actual data item that is stored in the cloud storage. So it has a tag and the encrypted data is there. So actually the data is encrypted using the server-aided MLE settings. It's a symmetric key that was shown in the overview slide I presented. And then these access structures have these privacy preserving components related, and these items that are encrypted using the PR-CP-ABE scheme. So for the write and ownership operation, we have the hash values for some random values included. And this is used during the proof of write operation to prove that someone has the right of, authorization for write operation. So to do that, it has to decrypt this component and send the hash of that decrypted value to the cloud server to prove that. So that's how the proof of write and ownership is achieved. And secure deduplication is achieved through the use of this outsourced data model. So you have meta storage. Suppose someone has D1, and first thing he does is to check if there is a tag. And tag is essentially a collision resistant hash value of D1. And then if the tag is not already there, then you use a message derived key to encrypt it and send it to the rapid storage. So you add that, you add the data in the storage also. And we are borrowing this Merkle-based path-overrun tree. We actually borrow path-overrun tree and extend it with Merkle tree components to store in the data to support secure data deduplication. If someone also, and then we create this reference to the tag. Someone else comes with the same data, wants to add, first thing it again does is to check if there's a matching tag. If there is, then it has now proof of right or proof of ownership. If it is passed, it can add the same data, but with different policy. So this is a separate policy added, but you don't need to have a separate encrypted value for that particular data because it's already there. So you just create the reference. So this is basic mechanism. If D1 is changed to D1 prime, then it has to create a separate component or replace this based on what semantics you want to achieve. So you could do that to add, remove the need for storing duplicate encrypted data. So this is proof of right access. I won't go into detail. The essential issue is once cloud storage sends the encrypted data, because the user already has the key from the trusted authority, it can decrypt this and prove that he has knowledge of, he has decryption key, the right decryption key. So that's how it is done. For proof of ownership, you could use the same type of protocol, but we extended Merkle tree-based mechanism. We find the path-overrun mechanism that has been proposed earlier with Merkle-based components to make it more effective. So to summarize, we provided PR-CP-ABE, which is shown to be secure against indistinguishable Trojan plain text attack. So if you're interested, please do read the conference or the journal version. We supported immediate attribute revocation by the re-encrypt mechanism. That re-encrypt mechanism is based on the current attribute sets, which is used by the trusted authority to create the escape2 in the previous example that is sent to the cloud service provider, which is used to encrypt the actual encrypted value stored there. We also supported access structure and access pattern privacy by integrating path-overrun. And overall, there's also always a concern about how we can prove the overall security of system with many components combined, and we try to use the universal composability theorem to show that. And that's detailed in the journal version. We have some experimental evaluation. I'll just quickly skim through to make sure I don't take too much time. So basically, the actual data is encrypted using symmetric key, which is based on server-aided MLE. The PR-CP-ABE mechanism is focused on encrypting that message key. So the focus is on that, but during that encryption, it involves a lot of computation, and that's what is captured here because there are a lot of attributes that may be involved. And so based on the attributes, the encryption time taken is linearly going up. So decryption is easier, but encryption is preparing all that different components that's involved in the attribute-based access policy. So that needs to be taken into account. So, yeah.
Can I ask a question now, or should we wait till the end?
Yeah, please go ahead, ask.
So here your rules for attribute-based access control is just AND, right? You don't have more complex things. So the policies are simply combination of attributes?
Oh, for these experiments, yeah. For experiments, we did basically different cases with AND logical conjunction.
Can it support like AND or some other more complex versions? Or it's just because of the underlying crypto, you can only support AND?
No, it can support AND or, you know,
Okay.
But for experiments, we just did these simple ones to see how the encryption or decryption time is impacted. So decryption is, of course, lower compared to encryption time. And there are some comparisons we did with other comparable approaches proposed that has immediate revocation scheme that typically uses some kind of re-encryption like we have in our case. And we see that on the encryption side, again, the performance is at the higher end, but then we are achieving privacy preserving access structure. So that adds a little bit to in the encryption part. On the decryption side, it is on the lower side compared to others. So we are within the comparable bounds of performance. This is a quick snapshot of key application. You know, when the user deals with key service and so forth, or different interactions, what is the level of communication, what size of data is used. And this has been typical way the research community provides some network data transmission requirements. And here we see our scheme is actually compromised. The best one is this one, but we are better than the other two. But again, we add the privacy preserving access structure. And this is a overall performance based on files, different file size and initial upload, read access, and so forth, just to show that it's something within the expected bound. It's not taking too much. So these are some other experiments we did, effect of file size and processing time and proportion of each processing component. Again, this is linear, so we are increasing file size for every next step. So this shows some linear increase with regards to the size of the file for this different operation. And also we did some experiment with the storage savings. And of course, storage savings means the deduplication aspect is quite constant because we don't really add the new files. We did it for different, this is simulated one based on some existing models like Gartner report that shows most of the, about 75% of the data stored in the cloud service provider is below 10 megabytes and so forth. To summarize this part, we try to provide an access control approach using privacy preserving revocable ciphertext policy attribute-based encryption. We integrated path-ORAM as part of it. We supported secure deduplication. But again, it is a integration of different pieces while we were adding new features like advanced access control, and which is right and ownership privileges, as well as privacy preserving access structure. But the concern is now again, trusted third parties. So it is single point of failure, even if it is decentralized, we have the trust issue. But at the same time, we were motivated by a lot of ongoing work on certificate transparency and the other work that it has inspired. So we were inspired by that line of work to also look at how we can address this trust issue with regards to the trusted entity that needs to support this mechanism. So we have more recent work that address the issue of trustworthy and transparent third-party authority, and how do we remove this reliance, fully trusting an authority to support this kind of mechanism. So in general, we tried to look at other schemes. Several schemes are there that have similar structure, that has those 4 basic phases: setup, key generation, encrypt, decrypt, and so on. And that involves a lot of interaction. So attribute-based is one. There are new access control encryption schemes being proposed that has similar structure. Functional encryption schemes needs something similar. So several emerging approaches have this third-party authority. So we were inspired by that certificate transparency to see how we can address these as well. Okay, so these are the typical common schemes in many of these other cryptographic schemes, and we wanted to focus on that. Several limitations are there for deployment of these schemes. There's a large and evolving sets of attributes. For example, in our CP-ABE scheme, we need to have TPA handle potentially very large number of attributes, even for one organization. If there are many, then that's a evolving environment. So organizations may add new attributes and so forth. It presents a single point of failure, which could be decentralized to address that issue. And there has been other proposals to do that, avoiding a single point of failure. But the key issue is, how do you establish the trustworthiness of TPA? And it could be insider trade issue, the TPA is compromised, or it has been mismanaged and so forth, that could result in messing up the overall process. So we were inspired by certificate transparency that really aimed at how, addressing the problem of SSL certificates. And there have been a lot of reports about how it could be fake, forged, or it could be issued. And so the certificate transparency initiated this research direction of how to provide openness and accountability for certificate authorities. And there have been follow-up work on transparency overlay. So some related work include conics and so on. The key idea here is how to provide auditing, logging, and monitoring services as part of this process. And how do you guarantee the characteristic that raises the trustworthiness of this process? And this is one report from more recent paper that shows within existing certificate authority infrastructure, even though only 0.2, very small percentage of total certificates violated the standards, it had this effect of many small authorities resulting in issuance of or misissuance of more than 10% of their respective certificates. So that has tremendous impact, even how they are used, given the fact that they are extensively used. So within our case, we have trusted third party engaged in several places. So it has to generate public parameters based on the attribute set. So it has a lot of elements inside in that set of phase. It has to provide those to the users, their attribute identities, simple IDs, and so on, that needs to be recorded. So we focused on these aspects to try to create this secure logging infrastructure. So before that, it's very easy to see that someone could easily mess up the overall process. For instance, here's an access policy example that requires attribute A, B, and C in this combination to be satisfied for any authorized access to this encrypted data. And the expected parameters are A, B, and C from these different authorities, if you consider collaborating trusted authorities. And so one authority could be compromised or could be an insider trade agent that messes up with the parameters. So instead of parameter B, it could provide D. So basically changing the professor as a required parameter to student. And so by using that public parameters set information, when data owner encrypts the data, it is actually now expecting student attribute to provide the access. So next time someone comes, this authority can give private key related to this one. Basically any student and some student who has other attributes also, one of the other two attributes also can access that, which was not the intended original policy. So this is the overall transparency framework we tried to come up with. There's a secure public loggers and PPAO and KSAO, these are the public parameter audit obligations. So when public parameters are created, the third-party authority has to log that as a commitment. And then once it sends to the public parameter, it can interact with the logger can interact with the client side to audit that and so forth. The same thing can be done for key service obligation parameter. When the client is accessing key service from the trusted entity. And so overall, the authority transparency framework has these six interactive protocols that involves interaction between loggers, trusted authority, and the client side. And so a lot of these are based on the originally, a lot of these interactive protocols are based on the original certificate transparency related work. But unique to us is this three-way protocol related to the two different components. So if you look at this, we have key service that needs to be logged, and this server and client and logger needs to be interacting to log the key service related obligations. And server also has to log the public parameter related obligations. And beyond that, other components are similar, of course, because of the different components that are logged. We actually log the interaction aspects as well as attribute identity or general identity aspects within this framework. So it creates a huge number of attribute identities that need to be logged and audited compared to the transparency overlay that actually formalized the certificate transparency solution. We have several of these components here. So this is rather simplified compared to ours in the sense that it has log, it has check entry protocols, inspect and Joshi protocols. So inspect protocol basically inspects the correctness of the audited logs. And there's a auditor and monitor Joshi protocol to try to make sure they find any inconsistencies in the audit log and so forth. And here it is focused primarily on the certificates, SSL, or the identity to public binding issue. But we have the interaction aspects that needs to be checked. So that's a nutshell, in nutshell, what we try to do. And the security guarantee provided is log consistency, unforgeable service, dishonest authority, for example, cannot force a key service by sending valid key service snapshots, but not really provide the key service to the clients. So we have shown that these are achieved. There's also non-fabrication. If someone, a dishonest authority or a client, wants to blame a logger for misbehavior, it should not be possible. So if we have provided details of these in there. And there are some experiments to just see how much performance overhead we achieve. And this is based on attributes in the policy, attributes in request set. Request set engages a lot of interactions, so we have to have additional performance overhead. So overall, we didn't have significant additions. And this is theoretical bandwidth cost during the interaction. That's some typical way others have done. And that's straightforward from the number of interaction and the sizes of different components that is involved. So I'll skip this and would like to spend a few minutes. So I think from my side, this applied crypto aspect was some of the initial work that we have done. Most of past work had been non-crypto access control. But given the nature, the reliance we now have with cloud computing, a lot of people are now feeling it's going to be much more important now, given the situation we're facing. This is something that we have to solve. There are decentralized approaches, multi-authority approaches that have been proposed, but I think their initial work in the sense that these transparency aspects have not been addressed. We have multi-cloud issue, edge computing, adding another architecture layer. How do we make it effective, efficient? IoT devices are adding more into the cloud services in terms of additional data that needs to be generated, managed. So I think there is a lot of work to be done. To make this practical, our effort was to try to have this integrated to include key aspects like deduplication issue, the access pattern as part of this. If you just have one part, there's always other threats to be worried about. Coming from the non-crypto side, I always worry about policy expressiveness aspects. Of course, we could do and or combination in the access structure, but then even in our case, we could have multiple user add access structure for the same data item, although data item is not duplicated. But how do we analyze these and to make sure that we have consistency and it does not create problems? And that's something that had been typical in the non-crypto side. Object granularity issue to attribute-based access control in general considers both subject and object attributes. How do we capture that? If you have object hierarchy, as we look at these aspects from non-crypto perspective, how do we manage that? How that affects, impacts the overall design of the solution and so on. And something that I haven't seen much about is when we have a lot of machine learning as a service and there's a lot of data in the cloud stored. Of course, if machine learning is to be run over such stored data that is protected by, for instance, attribute-based access control, what kind of can we really do it? What new solutions are needed to address that? And of course, the post-quantum secure approaches is definitely something that will be on the horizon. On the transparency side, I think there has been some good work and there's a momentum towards achieving, addressing that those kind of deployment issues in a much more concrete, provable way. But there is, I think, scalability issue. Even in our case, attribute could scale. What about resilience? Because we have different components. We showed that the protocols are in some way guaranteed to achieve those consistency and unforgeability aspects. But what other resiliency challenges come up is an issue. As soon as we have accountability, transparency aspects, how do we balance against privacy? In fact, in our work, we have a small privacy extension also, which I did not talk about. But these are, I think, some of the challenges I see from this particular pieces of work that we have recently done. And there has been some recent work that tried to address these deployment challenges and problems we see in this domain of transparency. Overall, I think in all of these environments, there's a significant integration issue. So that was one experience for us. We try to integrate different components. And if you don't have these, again, there are pieces that are assumed to be safe. So that's not the right approach, the way I see it. And obviously, efficiency challenges come in. How can we build component solutions that can be easily composed? You don't have to look at it again from holistic perspective so that you can piece them together and it becomes a rigid whole instead of being able to just simply compose as pieces of service. I think these are some challenges I see moving forward. So that is the end of my technical talk. If you will allow me quick 5 minutes, I'll just quickly overview that. Is that okay, Murat?
Yeah, please.
So a quick overview of secure and trustworthy cyberspace program that I've been very proud to be associated with for almost 1 year now. I started in September last year. It's truly a flagship research program that is really interdisciplinary in nature. So I get to work with people from 5 different directorates at least, and it focuses on foundational research on security and privacy in general in very broad way. So we have program directors in SATC team coming from education and human resources, engineering, maths and physical sciences, social, behavioral and economic sciences. And it is housed in computer and information science and engineering, particularly in CNS division, where I'm also primarily housed. So it's a huge number of people. These are typical topic areas mentioned in the solicitation. It doesn't have, a proposal doesn't need to just fall into any of these categories. These keep changing. We're currently also revising these topic areas to provide a guidance to the general community. This is our team coming from many directorates. Jeremy Epstein is our lead now. Nina has moved on to the Deputy Division Director. And so this is a big team representing broadly 5 different directorates. So we have core program educational project proposals that you can write and TTP. So there's a typo here. I think it's not 500, but I have another slide for you there. So small is up to 500K, 3 years, medium up to 1.2 typically. Education is actually 400K now. Frontier project, we just awarded 2 frontier projects. They're typically up to $10 million for 5 years. We look for really high and highly ambitious frontier, very far away thinking ideas in frontiers. And careers and CRI, they are always part of all the programs. Just for those who may be interested, there's new deadline for CRII. I think if you have subscribed to SATC email list, you must have received that. But there will be new deadlines for CRII's. Career was extended a little bit as well. So there's, we'll continue no deadline pilot. Many other core programs are actually also moving to no deadline pilot now, with some twist in the logistics. We stick to what we had this year. So you can submit up to 4 projects, proposals, 2 in the core area, 1 TTP, transition to practice, and 1 education. There's also other opportunities that you may want to check out. Just to mention a quick on the COVID-19, we were quite busy in April and May up to June with RAPID program. That was one response from NSF. SATC had about 2.5 million dedicated to funding RAPID projects. It has been archived, and we had some Congress CARES Act funding also included in that. besides rapid program, that's a typical one approach that NSF takes to address ongoing crisis. So it's typically 1 year funding. And there's also NSF Computing Innovation Fellows. If you're not familiar, please do check out. It's for those who are graduating now or just graduated because of the uncertainty of getting a faculty job or industry job. This provides support for postdoctoral studies. And there's also COVID-19 XP, High Performance Computing Consortium created, where NSF is a partner. This is a resource that would be useful. Also, I wanted to highlight that there's still an active eager, but this is a slightly research and education side. If you did not, there was 2 deadlines. If you did not submit to the earlier deadline, there is still an opportunity to submit in August, on August 31st. There's also upcoming workshop on next generation wireless technology security focus. So please look out for this. And if you have not subscribed to this list, please do that. We send occasional updates. And I have joined NSF last year. I joined last year. So if you have interest, please do reach out to me. I would be glad to share my experience. And NSF is a great opportunity to see a high-level view and also learn about few things at the federal level, and also a great opportunity to outreach to different communities. So with that, I end here and we'll open up for any questions. Thanks.
Thanks, James. Thanks very much. So let the audience, if there is any question from the audience, you just raise your hands or simple make a question. Well, I don't see any.
I have one question actually. If no one else, I wanted to give others a chance to ask a question.
Yeah,
So,
I also have a question after Murat, okay?
Okay, my question was simply, given that enforcing some policies, at least in my experience, give already without any encryption overhead, I guess this may only scale if the granularity is like a maybe large document level. I'm talking about the first part more. Or maybe you don't have too many objects to manage. So can you comment on like what do you envision with respect to a framework where you preserve all this privacy? So what granularity that you think scale this apply these techniques?
So object granularity, right?
So I mean, imagining like you have millions of records, I don't think you will be able to do attribute-based access control on encrypted. Each tuple is encrypted individually. So will that scale to millions of objects, or you are envisioning this to be done on like a database level or file level and so on?
Yeah, I think that's a very good problem, and that's why I also try to highlight that as object granularity issue is very important here. Right now, I think the typical focus is some data. So one thing I have to again mention is the attribute-based encryption component, the PR-CP-ABE, the keys generated by that does not directly encrypt the data. So we have symmetric key to encrypt the data. And that's like any general encryption. But with regards to providing access control, fine-grained access control on objects, that's, I think, a challenge, because you're creating an object, and you're defining access control on that. And it depends on what object you're editing. So it may be a huge object, but then the encryption cost is a symmetric encryption cost to be stored in the cloud service provider. So if you recall in the mechanism, the key service gives the user a private key related, the required key related to the CP-ABE scheme, but he actually needs to use that to decrypt the encrypted key, symmetric key, which is used to actually extract the data. So yeah, it's general encryption costs in terms of encrypting the data, but I agree with you, and that is also something I strongly feel is a big challenge in this kind of framework. So I guess the question is, are there newer approaches to address this fine granularity? In the non-crypto side, we typically sometimes also think about object hierarchy and fine-grained access control over this hierarchy of objects. So yeah, I agree that's a challenge, not addressed. I don't know if that fully answers your question.
But thank you. I think that's a good discussion to think about and direction to think about, I guess. Thank you.
So, yeah, I have a question, James, that I thought you mentioned about quantum computing. What is the connection between that and some of the work that you are doing on access control? Could you please elaborate on that? At the high level?
I mean, it's a general, I mean, quantum computing approach, it's a, I think in a way, very general future direction. So
Yeah.
the crypto-based solution, and we have specific cryptographic mechanism. Is it really post-quantum secure? It's not. So just to be thinking forward in terms of post-quantum era,
Yeah.
we need to probably think about approaches, even if similar to this, that is, post-quantum secure. So that's, I think, the key idea.
And whether you can do sort of these access controls, encryption and so on with quantum technology, that's another thing, right? For the speed.
That is true, yeah.
Yeah. Thank you.
Thanks. Any other questions from the audience?
Hi, this is Ron from UTSA.
Hi, Ram.
Hi, James. I have a question that's sort of a little bit general. So what do you think are some of the future challenges for access control? Could you speak about it from your own personal view and also with your current role at SACSI?
So I mean, that's a pretty open field. I think the issue that Murad just mentioned is one future challenge specific to access control, because if we are using outsourced computational environment where we have to encrypt data, then how do we do fine grain on the object side? We have not even, I guess, considered the object attributes as potential authorization rule components, right? In the non-crypto side, we have a lot of work along those lines. Another challenge maybe, is there any way to combine both the world in some way to achieve a much more realistic fine-grained access policy in outsourced computational environment? I'm not sure, but I think that may be some good question to ask. I'm more and more interested to learn about what might be actually challenges when you are having access control using this kind of encryption, and then you have machine learning services to be deployed on top of that. So that's another example. At the same time, we have, as Murad also indicated, we have explosion of data objects. And so how we can use machine learning to learn the access control policies in some way to help assist the authorization engine is potentially something I would consider worth exploring. I don't know if that answers.
Yeah, I mean, I was just curious. In particular, you had a point about machine learning on access control data, and there are you thinking about extracting access control policies, or are you thinking beyond that?
I mean, that both, I would say. There's also access control policy extraction, which I think I tried to make that as a point of the last comment at the end. But generally, when we talk about machine learning over encrypted data, there's been a lot of work, and we're doing some of that, how to do machine learning over encrypted data, but it's considered as one object, and you have access to it in encrypted form. But then encrypted data could be protected by a layer of access control like this one, with different permissions and so forth. Is that something to take into account as well? So that's something I have not done, but I keep wondering if it is even possible. Do we even need to raise that prospect?
Yeah, thank you.
Thank you. Thanks for the question. Thanks, James, for your presentation. Really, really good. Thanks again for accepting. And we right now in the schedule, we have a coffee break, a virtual coffee break, actually. So, and we're going to start the session at 10:30. So in this room, we are going to have session 1, and room